Hi guys, I wanted to make another AP Physics C Mechanics FRQ video. So this is from the 2019 exam, and this is from the set 1 FRQs, and this is question 1. So the information given to us is that in an experiment, students used video analysis to track the motion of an object falling vertically through a fluid in a glass cylinder. The object of m equals 12 grams is released from rest at the top of the column of fluid as shown above. The data for the speed v of the falling object as a function of time t are graphed on the grid below. The dashed curve represents the best fit chosen by the students for these data. Okay. So we're given a graph and we're given a picture of what's happening. So let's get started with our questions. All right, the first one is asking if the speed of the object is increasing, decreasing, or remaining the same. All right, well for this we can just use the graph provided to us. We're given a graph of speed and we can see that clearly our speed is increasing as it moves away from the x-axis. So I'm just going to say that my speed is increasing. Okay, moving on to part 2. So it tells us in a brief statement to describe the direction of the object's acceleration and how the magnitude of this acceleration changes as the object falls. All right, well, when we're talking about the direction of our acceleration, we know that we're going to be moving downwards, and I'm going to think about the net forces acting, or the forces acting on my object. So if this is my object here, we know we're of course going to have the force due to gravity. This will be constant. And then we're going to have the force of the fluid pushing up on the object. And so for a period of time, assuming this cylinder fluid is long enough, after a period of time, the amount of fluid pushing up on the object will equal the force of gravity, or the weight of the object as it falls. And so this is a lot like the concept of air resistance. And if you think about, if you were to drop an object in the presence of air resistance, it would fall, but eventually it would no longer have a net force acting on it as it falls, because the force of the air molecules pushing up on this object would equal the force of gravity pulling it down, and we'd be moving at a constant speed. So that's really the same idea that we have here with this mass in the fluid. But we can say that our acceleration will be pointing downwards until it will eventually equal 0. But in this question, they're looking for you to say down. So I'm going to say down for that part. And if we're talking about how the magnitude of the acceleration is changing as the object falls, well, we know that our acceleration is going to be decreasing. Because if you think about it, in a vacuum on Earth, the acceleration due to gravity is negative 9.81 meters per second squared, or about that. But that's with the absence of air resistance. So as our air resistance builds, the acceleration of this object down, the net force acting on it, will kind of start to decrease as our acceleration is decreasing. So we could say that the magnitude of the acceleration is decreasing. And another way we can kind of check this is if we look at the concavity of our speed graph. Well, we know the first time derivative of speed, or really we could say velocity in this case. We can say that the first time derivative of velocity is acceleration. So we know that acceleration is acting in the same direction as our speed, because as we can see by this graph, our object is speeding up as it falls. And so if something's speeding up, that means velocity and acceleration have the same sign, so they're acting in the same direction, which we can see here. But what we can also see is if we look at the concavity of our graph, well, we know concavity represents if the first derivative is increasing or decreasing. So in this case, my first derivative, which is acceleration, is positive. We know that because velocity is increasing. But we also know that my acceleration, if I was to graph it, it would be decreasing. It would be positive, but it would be decreasing, because the concavity, which is based on the sign of the second derivative, whether it's positive or negative, well, in this case, this is concave down, so my second derivative is negative. showing me that my first derivative, which is acceleration, is decreasing. So that's just another way we can think about our magnitude of acceleration changing. So I'm just going to write decreasing. All right, our next part is using the graph to calculate the approximate magnitude of acceleration at t equals 0.2 seconds. Well, like I just said, acceleration is the first time derivative of velocity. So I want to find the slope of my velocity graph to the best of my ability because I'm not given an actual equation to take the derivative of. But let's take a look at this. So if I draw around 0.2, I draw a line. Okay, I'm gonna use my y values as 0.8 and 0.6, and then for my x values, I'm gonna say like 0.23 and maybe 0.16. Okay, so if I say acceleration is equal to 0.8 minus 0.6 over 0.23 minus 0.1, I might say this graph let me try to redraw this line. Okay, I think that's a little better. So I'm actually going to say 0.14 as my second x time value, minus 0.14. Okay, and then this is equal to 2.22 meters per second squared. Okay, awesome. We're done with part A. Moving on to part B. I forgot to white this out, but for part B, we're given an equation for speed, which is v equals a times, in parentheses, 1 minus e to the negative bt. And we're given that a equals 1.18 and b equals 5 to the negative 1 seconds. And don't get too held up about the units on b here. The reason it is times s to the negative 1 is because we need our v to be in meters per second, and a is in meters per second. And so we need whatever's in our parentheses to essentially be unitless, so that way when we multiply it by units per second, we'll still have the correct units for speed. And because we have b being multiplied by t, I need a time value in my denominator of b to kind of cancel that out. Okay, so if we look at part 1, we're told to derive an expression for the magnitude of the vertical displacement of the falling object as a function of time t. Well, okay, I know that initially my initial position is equal to 0 because we're just dropping it. And so now I'm going to say that y, I'm not going to write my 0, but is equal to initially, which is 0 when I dropped it, times some t final times my velocity, which is a times 1 minus e to the negative bt times dt. All right, so this is equal to, I'll pull out this a, so that the a goes there. So that's equal to a times t plus e to the negative bt over b from 0 to t final. Okay, so this is equal to a times t final plus e to negative b t final over b, and then minus 0 plus e to the 0 over b. Okay, so this goes away. This is just 1. So this is equal to a times, well, if I factor out my 1 over b, I can just say t final. If I move this out of the way, t final plus my 1 over b times, in parentheses, e to the negative btf minus 1. Okay, I really had to squeeze that in, but hopefully you can see it and that makes sense. Okay, for part 2, we're told to derive an expression for the magnitude of the net force exerted on the object as it falls over time t. Okay, well, we know that our net force is equal to mass times acceleration. So first I'm going to write something for acceleration. So if I say velocity is equal to a, I'm just going to factor out this a to make it a bit easier. So if I do this, it's a minus a times e to the negative bt. Well, then I know my acceleration. This is a constant, so that goes away. So I basically get negative a times e to the negative bt times derivative of the inside is negative b. So I basically get ab e to the negative bt. So that's my acceleration. So then I just have to add my mass in. But I'm going to be careful with this and make sure, okay, when we were given our mass in grams. And so we always want to make sure that we're using our standard units, which is kilograms for this, because 1 Newton is a kilogram meters per second squared. So I'm going to say that my F net is equal to 0.012, that's just converting 12 grams to kilograms, times ABE to the negative BT. All right, and we're done with part B now. Okay, so then the students repeat the experiment with a taller glass cylinder that is filled with the same fluid, and it's tall enough so that the cylinder reaches a constant speed, or so that the object reaches a constant speed. Okay, so this is what I was explaining earlier with the acceleration, is that eventually as this object falls, the force of the water or the fluid, whatever it is, pushing up on our object will equal the force of gravity that's causing our object to be pulled down. So if we want to determine the constant speed of the object, okay, the easiest way to do this is we know that if we had basically an infinitely long cylinder, even just like what they're telling us, a cylinder that's tall enough for this to happen, we know that when t equals infinity and we had enough space for this object to just keep going down, we know that it'll eventually reach its terminal velocity or its constant speed at t equals infinity. It will have to be there. It'll of course get there before t equals infinity, but we know that at t equals infinity it'll be there. So if we just do the limit as t goes to infinity of my velocity, well, let's take a look at this. So if I have a times 1 minus e to the negative bt, okay, if basically this turns into infinity, this isn't proper notation, but then I would have a times 1 minus 1 over infinity. Well, we know 1 split into an infinite amount of groups. That's just 0. We call that 0. So then I'm left with a times 1 minus a times 0, so of course I'm just left with a. So I'm going to say that this is a. And I guess really, this is the justification. So here I should actually just say a, or you could say 1.18 meters per second, and then I would do my limit as my justification. Okay, so then if we were to determine the force exerted on the fluid at this time, well, okay, if we think about something reaching its terminal velocity, that means it's moving at a constant speed. And if we go back up and look way back at our forces acting on our object, well, I only have the force of the fluid and the force of gravity. So if this thing's net force is equal to 0 because it has no acceleration and it's moving at a constant speed, then these two forces must be equal. So I know that the force of the fluid must be equal to the weight of the object. So, okay, if I say this, I would say that force of the fluid must be equal to the mass of the object times gravity. And so I'm just going to say this is equal to 0.012 times little g. And the justification for my answer is just what I just said, where it reaches its terminal speed, and because the only vertical forces acting on it are the force of the fluid and the mass of the gravity, and our net force must be 0, then these two must be balanced, so they must be equal. And just if I was to solve this, I'll just say g is equal to 10 meters per second squared. Okay, so then I would just get 0.12 newtons as my force, as my resistive force. Okay, so that's it for this FRQ. I do think this one maybe was one of the harder ones. I just don't think that, at least in AP Physics, we're not really used to seeing things with resistance like this, but just stick to what you know. This is definitely a reasonable question once you really think through it. And we're on track. I'm at 1509, right as I said that. So we would be on track with our FRQs. I hope this video was helpful, and I'll see you in my next video.